Assalamualaikum warahmatullahi wabarakatuh. Ohayo gozaimasu minasan. Good morning, everyone. I hope you have a very pleasant morning and serenity. Welcome to SISTEM, Sharing Ilmiah Sains dan Teknologi Elektronika dan Manfaatnya. Volume 4 in 2024 held by Research Center for Electronics, National Research and Innovation Agency of Indonesia, with the topic Space and Earth Electromagnetic Monitoring for Secure Environment. It's an honor for me to inform you that among us here we have distinguished head of Research Center for Electronics, and in this occasion represented by the head of Electronics Circuit and Optoelectronics Research Group, Bapak Dr. Fajar Rahino Triputra ME. Distinguished speakers, Dr. Mitsunari Ozaki from Kanazawa University, and Bapak Dr. Insinyur Reza Septiawan from National Research and Innovation Agency of Indonesia. Distinguished moderator, Ibu Marcelina Ayuda Kristanti Titasari ST M.Sc, and all participants and guests. Ladies and gentlemen, please allow me first to read the agenda for today's webinar. The first agenda is the opening session, and the second, we will have a presentation and discussion session led by our moderator, and the last, the closing session. Ladies and gentlemen, please allow me to read the webinar's rules of conduct. All participants, please mute your Zoom meeting. If you have any question, please type your brief question in the chat box, or you can use the raise hand feature on the Zoom meeting. Please use the virtual background, and all participants are welcome to change your name into the name underscore your institution. And before we proceed our first agenda, I would like to invite all participants to sing the Indonesian National Anthem, Indonesia Raya. Ladies and gentlemen, we are now in the opening ceremony. As our first agenda, it's a great honor for me to invite the head of Research Center for Electronics, Bapak Yusuf Nur Wijayanto, to deliver some welcome remarks and opening the webinars officially. To Pak Yusuf, the time is yours.
Okay, thank you, Mbak Kriti. Can you hear me? Clear?
Yes, Pak. I can hear you clearly.
Thank you. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi ya. Good morning everyone and ohayo gozaimasu, our special guest. Alhamdulillah, thank you for the God for His mercy to us, so we can meet in here to study together, especially in the theme of space and earth electromagnetic monitoring and secure environment. Okay, today we have a special distinguished speakers from Kanazawa University by Professor Mitsunari Ozaki Sensei. He will give talk relating electric device up and upper atmospheric impact and energetic particles precipitation. And the second speaker is Dr. Reza Septiawan from Research Center for Electronics, National Research and Innovation Agency, BRIN Indonesia, with the theme of electromagnetic environment monitoring for secure electronic and habitable zones. Okay, the talk is very important, I think, in order to give a knowledge how to keep our earth and environmental from the effect of electromagnetic wave radiation and from electronic devices. Hopefully, through this webinar, we can study to design and realize electronic devices and systems and support the green technology for sustainability of the world. Thank you for the speaker for the interesting talk, and thank you also for the participant. And please use this moment to make interactive discussion and open for race collaboration relating electromagnetic for space and earth. Okay, thank you for all the organizer also to have this high impact webinar. I think my opening speech, and please enjoy for the webinar, and thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
We would like to express our gratitude to Pak Yusuf for the welcome and the opening remarks. Ladies and gentlemen, before we begin our main agenda, now we will be taking a picture together. So please, sir and madam, activate your camera and video function on your Zoom meeting. And I would like to invite the IT team to assist in taking pictures.
Okay, thank you, ladies and gentlemen. I will to take picture. Please open your cameras. Ready to start for slide 1. Okay, I think waiting is a moment. This one. 3, 2, 1. Slide 2. 3, 2, 1. And the last slide 3. 3, 2, 1. Okay, thank you, ladies and gentlemen. I return to MC, Bu Kristanti.
Okay, thank you, ladies and gentlemen, for your cooperation. Now we are reached to our main agenda for the webinar. But before that, I would like to remind all participants about the discussion session guides. Due to the limited time, the moderator will present only selected questions to the speakers during the discussion session. If you have any question, please type your brief question in the chat box. And you may also ask the question by activating the raise hand feature on your Zoom meeting until the moderators invites you to. In this webinar, we will have two speakers, Dr. Mitsunari Ozaki and Dr. Insinyur Reza Septiawan. And the presentation and discussion session will be presided over by the moderator, Ibu Marcelina Ayuda Kristanti Titasari, ST M.Sc, as the moderator. But before that, please allow me to read her biography first. Ibu Marcelina Ayuda Kristanti Titasari, ST M.Sc, is an engineer at the Research Center for Electronics, National Research and Innovation Agency of Indonesia. She completed her bachelor degree in telecommunication engineering at Brawijaya University and received her her master degree in communication engineering in University Birmingham of United Kingdom. And to Ibu Marcelina, I leave this session to you. The screen is now yours.
Okay, thank you very much, Mbak Kristanti, for the time. So I think we can start to our first speaker. Our first speaker is Mr. Mitsunari Ozaki, as we all know. Mr. Ozaki finished his bachelor's, master's, and doctoral degree at Kanazawa University in Japan. And his research field are about the plasma wave science and electromagnetic wave measurements engineering. Mr. Mitsunori Ozaki or Mr. Ozaki have some several professional history like we can see here. So he is a member of the GARE, Japanese Antarctic Research Expedition. And then he's also the researcher at the Kanazawa University in Japan. And currently he's also a co-investigator of plasma wave instrument of the Arase satellite for geospace. And also he's a co-investigator of plasma wave instrument of the MEO spacecraft. Okay, so I think it's the time to Mr. Ozaki to start his presentation. To Mr. Ozaki, the time is yours.
Good morning, everyone.
Good morning.
So first, I'd like to share my screen. Can you see my screen?
Yes, I see.
Okay, so yeah. Okay, so I'm Mitsunari Ozaki from Kanazawa University. So I'd like to thank the session conveners for this nice webinar. So today I'd like to talk about the electric devices and upper atmospheric impact on energy particle precipitation from geospace. Okay, can I start my talk?
Yeah, sure.
Okay. Okay, this is a simple my self-introduction. Okay, so yeah, I was a nice opportunity. I was a member of Japanese Antarctic research expedition in this duration. Now I'm a researcher at Kanazawa University. My research field is the plasma wave science and engineering. Also, I'm interested in the electromagnetic wave measurement engineering. So I'd like to introduce the Japanese Antarctic research expedition. This is the previous picture when I was a member of the Japanese Antarctic research expedition. So this JARE is for the Japan has performed various scientific observations at Showa Station in Antarctica and the surrounding area. To go to the Antarctica first, we go to Australia by airplane. After that, we go to Antarctica by this ship. So yeah, this is the first. The second, this is a movie. The 2 days later from Australia. The first we had the big storm around the Australia. The last movie taken at here. So taking it here, but we had a very big wave. And this is 11 days later, we see a small ices on the sea. And this 12 days later, the sea is almost ice. And this is 15 days later from the Australia. The sea is almost ice, and the thickness is almost 1 or 2 meters. So in this situation, we cannot go to Antarctica by ship. So I'd like to show movie. Now we go back to the SIP from the front side. So that sorry, and I'd like to skip the movie. The very thick ice. So usually we cannot go to the SIP by so we back to the SIP. Then after that SIP go to front side. Then SIP attack to the ice, and we will break the ice. So we gradually go to Antarctica. So finally we got show station like this. So, how cold at show station in Antarctica? This is the average temperature variations. The horizontal axis is the month, and the vertical axis the average temperature. And in 2006, the blue is the Kanazawa city in Japan, and the pink curves is for the show stations. Show station in the South Pole, so the season is different at the northern hemisphere. The dry and August around here, northern hemisphere is the summertime, but dry and around August in South Pole, this is the winter time. And the show stations, the whole month, the average temperature is less than 0 degrees. So I'd like to show a small experiment in show stations. I said the temperature is minus 20 degrees. This is a wet towel. Now is wetting. Please wait a few, several 10 seconds. The wet towel is cold. Yes. Finally, the wet towel was frozen. Just a few 10 seconds. Also, around Antarctica, we have a snowstorm called the blizzard. This is a snowstorm in Antarctica. We have there are many snows and a very strong wind. So after the blizzard, if we open the door, yep. After that, we have a snow wall like this. So the Antarctica is a very interesting. So in Antarctica, I studied northern light aurora and the natural electromagnetic wave coming from the geospace. This is a picture taken by myself. We see a Korea aurora like this. Yeah, I like these pictures. So today I'd like to talk about the mesospheric ozone destructions. Mesosphere is around here. The altitude is 50 to 80 kilometers. And this ozone destruction is related to the plasma wave activity in geospace. So the plasma waves are generated at the altitude around 36,000 kilometers. So the altitude is a big difference, but we showed a direct link between them. So what is a geospace? The geospace is space area up to the geostationary orbit. So that you know there are many commercial satellites in geospace, and in geospace it's not vacuum. We have a plasma. If the plasmas have higher energy, then plasma becomes radiation. So that Earth has magnetic field, as you know. So the plasma particle is affected by the Lorentz force from the Earth's magnetic field. So the plasma shows a cyclotron motion, a bounce motion, and drift motion like this movie. The blue is the particle orbit around the Earth. So like this movie, usually the plasma cannot penetrate to the atmosphere. So the higher energy plasma is the radiation. So the relativistic energy plasma in geospace can penetrate the satellite metal shield and cause damage to the semiconductors of the satellite electronics. So it's important study on the radiation effect for the electric devices. And a part of the plasma can precipitate to the atmosphere, then aurora are illuminated. So aurora is beautiful, but aurora is the key phenomenon for understanding the plasma dynamics in geospace. So there are many important plasma waves in geospace, and the plasma waves can push energetic plasma to the atmosphere. So precipitating plasmas penetrate to the atmosphere, then illuminate it or phenomenon. So today, I'd like to talk about electric devices and atmospheric impact by relativistic electron precipitation driven by plasma waves in geospace. So first, I would like to introduce two important effects of the radiations on electric devices. One is total dose effect. The other is single event effect. The total dose effects, the gradual degradations of the LSI circuit by a long exposure of the weak radiation. On the other hand, the single event effect that causes a program or memory error just only by a one high energy particle. So first, I'd like to introduce the effect of the total dose effect for the transistors. As you know, this is the simple NMOS transistor. Here is a gate, a drain, and source. And now we connected to the source to the ground. So this is just a simple source grounded circuit. Now we apply the positive voltage at the drain, and gate voltage equals 0. So it means this transistor is off state. So we don't have the drain current in this situation. But of course, we apply the positive gate voltage in these situations. We make a channel between the source to drain, then drain current drastically through to the source side, so we can get the on state in the transistor. So this is the horizontal axis, the gate voltage, and the vertical axis, the drain current. So if we apply the large as the threshold amplitude, we can get the sufficient drain current like this. But this is a simple situation. But if we have a radiation effect, then radiations make the ionization. So the electron hole pairs are generated by increases of the radiation to the gate oxide field around here. And the radiation attacked to the gate oxide film, we have the ionization. So we have electron hole pairs. Then electrons move rapidly because the electron is very, very light. So electron moves rapidly, but hole moves slowly due to the heavy mass in comparison with the electron. So the moving holes are captured at the lattice defects in the gate oxide film. So the captured holes become a positive charge. So finally, the positive charge are stored and the positive charge are generated at the boundary phase between the Si and SiO2. So then, if we have a zero gate voltage, but effect of the radiation, we have a positive charge around the SiO2. So if we do not apply the gate voltage, but effect of the radiation, transistor may be turned on by the effect of the radiation. This is the total dose effect. So in the radiation, transistor characteristics gradually change, like this figure. The threshold voltage gradually decreases by the effect of the radiation. This is the total dose effect. And second is the single event effect. Single event effect are higher, only one high energy particle attack to the transistor. This figure shows a simple Islam diagram. As you know, if just only one particle, but this is a very high energy particle, then high energy particle attack to the only one transistor, then such a high energy particles make a high dense carrier path like this. Then the transistor states change. So the memory state reverse. So this is the single event effect. So in the radiations, the transistor can be drastically affected from the space radiation. So the provision techniques are very, very important in operating the electronic devices in space. So next, I'd like to talk about the ozone destruction by the effect of the relativistic electron precipitation. So not only the electric device, energetic particle impact to the atmosphere. So here I would like to show a special aurora. And this is the it's called the isolated proton aurora. So this aurora includes both precipitations of low energy protons and relativistic electrons. By using this special aurora, we overcome the difficulty for identifying the locations and durations of the relativistic electron precipitation using the special aurora. The proton precipitation, the low energy proton precipitation causes the aurora. And this video shows an example of special aurora. This video is observed in Canada. And the upper panel are for all sky images in different wavelengths. And the bottom panel is for the plasma waves observed on the ground. And the red area indicates the strong plasma waves. So if we observe the strong plasma waves, then we see a clear auroral illumination like this. So we see a clear correspondence between the plasma wave activity and the auroral phenomenon. So this special type aurora shows the locations and the durations of the relativistic electron precipitation from the zero space. So we can identify the when, where, how long in the relativistic electron precipitation using the special aurora. So this special aurora is very important for monitoring the relativistic electron precipitation. Such relativistic electrons can ionize the atmosphere. Then they impact the atmospheric chemistry. So we evaluate how much atmospheric impact just below this special type aurora. So we use these satellite measurement data sets for locations of the special aurora. We use the satellite images. For relativistic electron precipitation, we use plasma particle detectors from the satellite. For the plasma waves can propagate to the ground side along the magnetic field line, so we can observe the plasma waves on the ground station. So we use the plasma wave data observed on the ground. So how much ozone impact in this study? We use the ozone data measured by the satellite. And this is today I'd like to show an example event during non-solar storm time. This very, very quiet time. And this is a special type aurora. We see a clear special type aurora around here. This is taken by the satellite around the Antarctica. So next is this blue indicates the relativistic electron precipitation by satellite. We see clear correspondence between the high count rate of the relativistic electron precipitation only around the special type aurora around here. So it means this special type aurora indicates the locations of the relativistic electron precipitation. Okay, next is the ozone observations. The red is the high density, the blue is the low density, the ozone. And this result measured by the satellite. So around here, we see a clear ozone loss near the special type aurora. But around here, we do not see a ozone loss near the special type aurora. So I would like to show the reason. So the bottom figure shows the plasma wave activity observed on the ground. We see a clear plasma wave activity. But around here, we looks like no ozone loss. But this time is here. So it means in this ozone observations, we do not have the active plasma waves. So after this time, the plasma waves becomes active. So the ozone variations below the special type aurora was observed to more rapidly decrease around 1 hour after the generations of these active plasma waves. So in this satellite observation, we do not have a active plasma wave. So we do not observe the sudden ozone loss around here. But around here, we have the strong plasma wave. So we have the sudden ozone loss only around the special type aurora. Also, this figure shows the vertical ozone profiles passing through the special type aurora locations. The vertical axis is the altitude, and the horizontal axis shows spatial locations. So also this the right hand side, the vertical axis is the altitude, and the horizontal axis is the ozone density. And the green, red, blue lines, these are for the vertical profile, ozone profile crossing the auroral locations. But the black curves indicate the monthly mean value. So only passing the special type aurora, a significant ozone loss, we identify in the mesosphere region. So the average ozone loss at the mesosphere crossing the special type aurora locations shows about 51% degrees from the monthly mean value. So we have a large ozone loss only around the special type aurora location. It means relativistic electron precipitation ionized the atmosphere. Then ionized atmosphere changes the atmospheric chemistry. Then we observe the strong ozone loss. Okay, this is the summary today's topic. The radiation from the geospace, they may be affect to the electric devices and atmospheric chemical impact. Especially a clear spatial correspondence between the mesospheric ozone loss and special type aurora was identified using the special type aurora and the plasma wave activity during the non-solar storm condition. So the monitoring of the high energy particle around the space is very, very important. Okay, that's all for my talk. Thank you for your kind attention.
Okay, thank you very much for your presentation, Mr. Ozaki. I think there was a very spectacular experience, yeah, to do a research about aurora in Antarctic, right?
Yeah, Antarctica, especially the Antarctica is a very, very
Antarctica is
cold.
very special, yeah, I guess. Okay, now I would like to ask for the participants to maybe want to ask some questions to Mr. Ozaki. If everyone want to ask, you can click the raise hand button.
Sorry, Bu Marcelina.
Yeah.
Can I ask? But I don't know how to raise the hands in
Oh
the.
yeah, yeah.
Is it
It's fine,
possible?
Reza. Yeah.
Yeah.
You can ask, yeah.
Thank you, Bu Marcelina. Thank you so much for Dr. Ozaki for a good, very interesting presentation. I would
My
like to
pleasure.
know,
Yeah.
yeah, I would like to know which one is the more uh, more experience, like which one is the occur occur more between the graduation effect or the single event effect when there is some disturbance in the space magnetic, just to make sure which one we would like to focus on. So for example, if we would like to focus on the single event effect, then mostly what we are doing is actually for the navigation data. So if it is a single event effect, probably it is very, very important because it can change the memory, yeah, the binaries. So in that case, maybe it is very crucial for us. So please, it is my question: which one is more happen more frequently in that case between these two? Thank you.
Yeah, it's a nice question. Thank you so much. Both for my side, both the total dose effect and the single event effect is both is very very important. But as you said, that single event effect directly affect the data memory or program memory on board the satellite computer. So sometimes it would be cause a big effect on the satellite onboard computer. So the provisions for the single event effect is very very important. But the single event attacked by high energy particle. So usually we cannot shielding such a high energy particle. So to mitigate the single event effect, usually we install three systems to decide which is the majority. Because if we have the some single event effect, the memory data will change. So we cannot identify the memory data if we have a single event effect. So to identify the single event effect, sometimes we install the same system, three or like this. Then we take the majority. Two data is the same, one data is different. In such case, we may have a single event effect. So one data is not correct. So we can detect the single event effect. So it's a not good idea, but to mitigate the effect of the single event effect, usually sometimes we install the three same systems to identify, to mitigate the single event effect, because the single event effect cannot shielding using the heavy metals.
Oh,
Yeah,
thank you
it's
so much.
my idea.
Yeah. Thank you so much. In that case, it is a redundancy that three the similar systems will be installed. It means
Yeah,
that just to compare between these three, which one is
yes.
the most okay, right?
Yeah.
And you mentioned that it is not possible. It is not. It's not possible to be shielded. Is it because the high radiancy that they can get? How big is the radiancy that make that it cannot be shielded?
Yeah. Such the single event effect will be happened by very very high energy particle. So such a very very high energy particle usually we cannot shielding using a metal shield. So should um, we should uh, uh, we should uh, accept happening the such a single event effect. So sometimes we should identify the single event effect using the same three instruments or same three memories to compare them.
Yeah. Uh, Do you have some threshold value for example, was it the quantity, the threshold value of the radiation that it is it can be solved by using shielding, and which one is not? You,
Sorry,
no?
I'm not sure the detailed value,
Okay,
but
yeah.
yeah, but if I have some information, I will send to you later.
Thank you so much. Thank you so much. Hey, thank you, Bu Marcelina.
Yeah, thank you so much.
Yeah, thank you, Pak Reza, for the question, and also Mr. Ozaki for the answer. Is there anyone else that want to ask some question or have a discussion with Mr. Ozaki?
Yeah, I have question for
Oh,
Marcelina.
yeah, the time is yours. Start
Yeah.
my.
Thank you, Mr. Ozaki. It's
Thank you so
very
much.
interesting. Very interesting. I would like to know if the difference, no, the different material from the transistor will be affected also. I mean, what is the degree of impact for different kind of transistor or MOSFET in
Of course, yes. I
because
showed a simple example for the simple NMOS transistor. But
yeah, but
if we use the SOI system, we can mitigate the total dose effect and total dose effect. So
okay, thank you. Okay, so with a different material, we can also anticipate the problem of radiation. Yeah.
yes, you are right.
Thank you.
Yes.
Okay, thank you, Pak Michael. Thank you, Mr. Ozaki. Is there any other question? Okay, to Mr. Muhammad Iqbal, Mas Iqbal.
Okay. Thank you, Mr. Ozaki. Sorry. I have one question. How much the time that you need to run the experiment? I mean, is it, and second, is it reproducible? I mean, we can recreate the experiment more or not? Because I think it's really hard to do such kind of experiment, especially in the extreme conditions. So yeah, that is my questions. The first one is how much the time that you need to get a right measurement, and second, do the experiment are repeatable?
Sorry, I'd like to know the which topic, the for the electric device or the ozone loss.
The ozone loss.
Okay, ozone loss. For the ozone loss, we use the nominal data measured by the many satellites. So it's a free. I'm not sure the free, but we can use these satellite data. So this data is publicly open, so we can suddenly identify such ozone loss event using the these public satellite data.
Okay.
So in my study, after the active plasma waves, just 10 minutes or after the just 1 hour later, we observe the sudden ozone loss. So about less than 1 hour, we can identify such a sudden ozone loss by the effect of the energetic particle precipitation from the geospace.
Okay, I think that's all my questions from me. Thank you, sir.
Thank you so much. Yeah.
Thank you, Mas Iqbal, for the question. Thank you, Mr. Ozaki. Okay, is there any other question? Okay, if not, maybe I want to ask you one last question, Mr. Ozaki. And I think it's kind of different from your presentation, but I read about your publication, and I think you wrote about something about meta surface. Is that right?
Yeah.
Yeah. So because of my research is about meta surface, so I want to ask you about the usage of the meta surface in your research. Is it probably for the observer or something, or anything you can explain? Yeah. Maybe you can explain more about the meta surface usage in your research.
Yeah, meta surface is artificial material to control the electromagnetic waves. So the meta surface is one candidate of the artificial control, the plasma wave or plasma environment. So sometimes the meta surface can control the polarization of the electromagnetic waves, or sometimes the metal surface make us optical lens for the electromagnetic waves. So we can control the electromagnetic waves using the metal surface, metamaterials. So such application using the metal surface, we may make unique plasma waves using the metal surface, metamaterial. Then we can control the plasma populations around the Earth. So metal surface, one possibility for artificial control of the plasma waves or plasma environment. It's my simple idea.
Okay, I understand. What about absorber? Is it possible to use the metal surface?
Yes, of course, metal surface can observe the electromagnetic power.
For plasma wave as well.
Yeah,
Oh,
of course.
Okay, thank you. I think that's all.
Yep, thank you so much.
Yeah, thank you so much for your answer. I'm sorry. Is there anyone else that want to ask question to Mr. Ozaki? If not, so I want to thank to Mr. Ozaki for the time, for the presentation, and for the discussion. And thank you very much. And maybe we can have a discussion later about this, about your research. And next, I want to introduce our next speaker. Our next speaker is Pak Reza Septiawan. So Pak Reza finished his study in Electrotechnic in TU Delft and also School of IT in Bonn University. And Pak Reza is a research group leader of the Secure Electronics Design in a research group of Center of Electronics. Pak Reza is my Kepala KR, to be honest. And now Pak Reza doing some research about the development of a field of secure electronic design, especially in relation to the integrity of CNS, communication, navigation, surveillance, and also in GRNSS integrity, and also in autonomous electric vehicle. And the last one, you'll also do develop a ground monitoring station for potential hazardous electromagnetic environment. Maybe it is a time for Pak Reza to give a presentation to us. Pak Reza, the time is yours.
Thank you, Bu Marcelina. I would like to share my presentation. Just a moment, this one. Okay. Okay, thank you so much. So thank you, Bu Marcelina. So I would like in my presentation is mostly about in my research group, we would like to investigate what is the risk if some electromagnetic disturbance come into our electronic devices. So in that case, we need to monitor what are the potential disturbance can disturb our electronic devices. So instead of only monitoring the environment outside the electronic devices, we also need to observe and monitor the disturbance that coming inside the electronic devices. So in that case, we have two topics to be discussed in the presentation. The first one is more about the disturbance from outside electronic devices, and the second one is more about how can we design an artificial magnetic shielding for a habitable zone. So in the first, this one is more about protecting our electronic devices, and the second one is more to others than protecting our devices. Is it possible that we can design a space with an artificial magnetosphere that make us possible to uh, to live on live in. For example, an organic can live in Earth because there is some protection, the magnetic shielding that protect our Earth from any radiation from outside the Earth. So in this case, the in this second topic, I would like to raise some interest in the research about how can we artificial made a magnetic field that make us possible to live in. So we can develop receivers and then also smart agri and agriculture. Um, so I think this is just the introduction of our institution, National Research and Innovation Agency. It has like some departments, and one of them is about in Department of Electronic and Information. That's the one that we are in. So this is the research centers that we have in the BRIN. So we have sensor and actuatory devices, thermoelectric, secure electronic design, electronic optical, embedded electronic system, intelligent electronic systems. So we do some research in this area. From my research group, we have 11 members. So one of them is Abu Marcel, the host today, the moderator. So in this, the first part of my presentation about the electromagnetic the disturbance in electronic devices, I would like to show about how important it is to protect our electronic devices from any electromagnetic disturbance, because the safety comes from the good quality of electronic devices. So if the electronic devices uh, has some failure because of electromagnetic disturbance, it can impact on our safety. So that's why we would like to do some testing to ensure that the product performance, the quality of the electronic devices can comply on some standard. So in our case, we are more interested in the electronic vehicle. So we would like to measure the monitoring some disturbance that come into the electronic devices, not only from outside the electronic devices, but also from inside of the electronic devices. So this one is the measurement that we are doing to monitor the electromagnetic disturbance from outside. So we monitor the electromagnetic in some area in Serpong, in our laboratory. So we see that different place, different location has different electromagnetic characteristics. So in that case, we cannot make some assumption that in every place, in every location, that the electromagnetic environment will be the same. So it is useful to look at specific locations with specific electromagnetic environment characteristics. In that case, we will know how we can handle, how can we mitigate, the, how can we minimize the disturbance in the electromagnetic. This is from when we measure the environment of electromagnetic in different area, and we compare with the environment inside our chamber. So we can make a difference. We can make a study whether the performance of our electronic devices is more uh, risky if we will try to use in some location. So these are some of the pre-compliance testing that we are doing for electronic devices. Mostly what we are doing is in the navigation, aid devices like ADSB, ICE, etc. So the signals from the navigation satellites are really um, um, is very sensitive into the electromagnetic disturbance. So it is useful to do a lot of testing into the electronic devices related to the navigation system, because for example, GNSS is very vulnerable because the signal is uh, very weak. So not it doesn't have to be a very strong disturbance can disturb our navigation uh, signal. In that case, we need to make sure that our GNSS devices uh, has a very good shielding, etc. So the other the another thing that we are doing is more about the disturbance that coming from inside. This is another example in the area of Serpong, in the area of our laboratory, that we can see the signals, the disturbance of electromagnetic is very um, varies, very dynamics. In that case, when we would like to travel with electric vehicle, we have to make sure that our navigation system is not disturbed by this different source of potential disturbance, electromagnetic disturbance. So this is an example of disturbance that can come up into our GNSS system. So this is the frequency of the L1 and L2. In this graph, we can see that it is no disturbance at all at L1, L2, but it is because the L1 and signal L1 and L2 from the GNSS is very weak. It has to be ensured that any signals that higher than minus 70 dBm that can occur in the L1 and L2, if either it is in band or out band of any other frequencies, has to be measured. So we have to make some shielding on it. We do also some monitoring in the area of Serpong, industrial area, for different frequencies. This is from Pak Fajar. And this is the facilities in our laboratory to do some per-compliance testing of the electronic devices to ensure that they don't have some electromagnetic disturbance emission from the electronic devices. We have for the radiated emission and also for the conducted immunity. This is for the magnetic field immunity. And we have also which one? This is for the harmonics and flicker. So this is the facilities that we have. The standard that we are using is the IEC 61043 for the radiated immunity. So we can test how strong our devices in potential AM disturbance. So in the environment that has very strong AM disturbance can disturb our electronic devices. This is to perform some testing for the surge, burst, and fast transient. So, for example, the power system in our network is not stable. If there is some uh, burst disturbance coming into our device, we would like to make sure that our device is still working properly. This is for conducting immunity. So we can do um, some disturbance into the wiring of two devices, and then we check whether the performance of the devices are still the same. So that's more about the electronic devices. So we check the emission from the electronic devices, and then we make sure that our electronic devices is cannot be disturbed by some electromagnetic disturbance emission. The second topic is more about how can we design a space that has some magnetic field that will protect us from any potential magnetic disturbance. So we would like to ensure that in this space there is a possibility that we can grow some uh, organic organic system. So for example, uh, we can we can grow some plants, we can grow some uh, anything. So we would like to ensure the safe and sustainable habitable zones in any potential AM disturbance or loss of AM earth shielding. So how can we do that? So first of all, we need to monitor and the near real-time monitoring of the electromagnetic in the area, and then we design an artificial magnetic shielding. So this is also one of the question of Bu Marcelina, whether we can have some kind of shielding that we can control by using meta material. So we can use this artificial magnetic shielding to design a habitable zone by developing low frequency receivers and also developing a smart agri and aquaculture. So this is the measurement. We try to monitor a real-time monitoring of the electromagnetic and develop of the very low frequency receiver and also smart and agriculture. This is the monitoring system design. We use antenna, splitter, and then this is just because the GNSS is free and it is always available. So this is actually one of the reference that we would like to use. So the GNSS satellites are orbiting in about like 24,000 kilometers above our Earth. So in that case, it will travel along uh, via the ionosphere, atmospheric, until our ground receiver. In that case, the long path that they experience can give us more information about what are the situation on these layers, on the ozone layers, on the ionospheric layers, and etc. So when we receive our signal, it is a lot of information. It's not only for about positioning, timing, or navigation, but it's also for monitoring the condition of the space. And it is also free, and so many satellites are now already uh, in the constellation that we can tap the signal. So this is one part, and the second part is more about the frequencies of the signals, the radio frequencies, microwave frequencies that we would like to receive. So from both of these, from the GNS receiver and also uh, uh, from the receivers, the radio microwave receivers, we combine, and when we evaluate to monitor the condition um of our atmospheric, our ionospheric, and all above 2,000 to 20,000 kilometers based on the data that we receive in on ground uh, ground monitoring. So this is the design. So we have antennas, array of antennas, and then we do some shifting to ensure that we can combine all of the signals together, and then we analyze the signals. So based on these signals, we can know what happened with the signals from the satellite until the ground, and what are in between, what condition that the signals from the satellite into the ground, the traveling condition of the signal from the satellite into the ground. And then the second, this is the first concept of design. We would like to have a more than one satellite ground monitoring system to compare the phase, etc. So as you mentioned, as from the doctor mentioned already, that we also monitoring from the inside the satellite. So fortunately, our Lapan, there's our JAXA in Indonesia, they have already 4 satellites traveling around the Earth in LEO, about 500 kilometers above Earth. And some of the sensors that they have is the magnetometer. So in that case, we also ask them to gather these signals in 2023, but unfortunately we haven't analyzed the signal yet. But hopefully we can compare the signals, the magnetometer values that received in the satellites, compare into the data that we receive in the ground at the same time. So we already tapped the signals in 2023 until now, about 6 months. So this is some data acquisitions that we've done in Serpong. So we measure about the magnetic values, and hopefully we can compare it with the data that we get from satellite, Lapan satellites. So this is the monitoring system in Serpong. We would like to have a remote signal monitoring. So this is the concept of the continuous habitable zone that we would like to have. So we'd like to have some kind of, or maybe another, so that's this one, maybe small. This is Earth. So we'd like to have at least one shielding chamber, that can protect us from the radiation. And then we would like to have some antennas to receive and to generate some artificial magnet uh, around this chamber. And also we would like to have some smart agriculture, smart aquaculture inside the chamber that we can monitor. So in that case, we have 3 subsystems. One is the chamber itself. The second one is the antennas that we would like to where we can generate the magnet, and also inside the living organism. So this is the references that we are looking at from some of the systems that already done. So hopefully, based on that, these are the 3 systems that this 3 subsystems that we are developing now in progress. The first one is the shielding chamber. So hopefully it can shield a bit probably like more can protect from strong radiation. And the second one is to generate magnetic shield. So instead of only having this, some kind of radiation shielding, we would like to generate also some magnetic sphere, artificial magnetic sphere. And inside, we would like to have this living organism, smart agri aquaculture that we can habitate over here. So there are the 3 subsystems that we are now doing. So this the first subsystem, the second subsystem, and the third one for generating the magnetosphere. So hopefully we will continue with this, and then with the information that we get from Dr. Um, from Kanazawa, probably we can do more research in this area. So Pak Budi probably can pursue his doctoral degree, maybe in this kind of this area. So I think that's all. So at last, I would like to identify what type of research that we can do together. For example, the identification of terrestrial and space AM sources, the AM energy harvesting, wireless power transfer, or artificial EM shield to improve habitable zone level using energy and cosmic sources. I think that's all about from my West presentation. Thank you for the time. Hope will be useful for us. Thank you.
Thank you very much, Reza, for the presentation. I think we can see that there's lots of research in our research group, right? And maybe you will open for another member to join us, or I think it's enough for us with this member.
Yeah. Hopefully there will be a lot of interest in our research group.
More
Yeah.
people to interest, yeah.
Yeah.
So I will open the discussion time for the participant. If anyone want to ask some question, you can just ask or raise your hand. Okay, Mr. Ozaki, the time is yours.
Thank you so much for very interesting your talk.
Thank
Yeah,
you.
especially I have an interesting about the artificial electromagnetic shielding for smart agriculture. Now, do you have a difference with and without artificial electromagnetic shielding in the seed growing like that?
Yes, thank you, Dr. Ozaki. Currently, we haven't measured in the real life the impact of electromagnetic into the plant grow. But we done before uh, in not really in a shielding chamber, but it is in a controllable chamber. We One of them is open, so it is everything in the environment, every electromagnetic in the environment can come into the plant. But and the second one is a shield by using we use at the time a glass with some aluminum foil, and in that case, the one that we grow in the glass with aluminum foil is really cannot live long, but compared to the other one that without shielding. So in that case, I'm not sure whether it is um, the method that we are using is not right at the time, because the light cannot come through the aluminum foil at the time. So maybe that's also the reason. So we are still thinking how can we do measuring the effect of the electromagnetic into the growth of the plant, but not minimizing the effect of the sunlight, because that's the most important thing. So until now, we still need the sunlight until now. So we try also the UV lights, but it's not really comparable at the time. So I think um, our research right now, um, we are doing automatic uh, autonomous monitoring control system for agri and aquaculture, just to ensure that we can monitor by using sensors all of the parameters. So in that case, we know what parameters are very, very important into the growth of the plant. And then we need to make sure that we don't minimize these parameters when we would like to shield our electromagnetic field. I think that's the phase of our research till now,
Yeah,
Dr.
but
Saki.
yeah,
Yeah.
very interesting. Yeah, in future
Yeah.
we will have lunar or Mars experiment. So this topic is very important for near future. Thank you so much.
Thank you, Dr. Ozaki. So maybe in the future we can. What I'm thinking about is we we can we can do some proposal
Mhm,
to have some kind like to launch a small satellite, nano, micro, etc.
mhm,
And then inside we can have some shielding chamber that can we do the same lunar and solar plantation probably.
mhm. Yeah, it's
Yeah,
very interesting.
yeah. Thank you.
Thank you so
Thank you,
much.
Dr. Saki.
Okay, thank you, Ms. Ozaki and Pak Reza. Anyone else want to have a discussion for our next speaker?
Just for information, maybe Marcelina, if there is no question, still no question, in our research group, we have two big uh, activities here. The first one is electric vehicle for mobility, and the second one is for the autonomous monitoring control system. So actually, these two topics are related. So the first one is to monitor the electromagnetic, and the second one is to ensure that they can live without the disturbance of the electromagnetic. So anyone that will have interest in this topic or the research topic is welcome.
Yeah. So we open for everyone here. If want to join us or maybe have interesting and have a discussion with Pak Reza especially, maybe you can contact Pak Reza directly.
Yeah.
Okay.
Yeah, thank you.
If there is no other question for the participants, or maybe Pak Michael want to ask something?
Yeah, I have one question
Okay.
about the artificial shield. Yeah. Do you have the shape or what's the volume of the shield? I mean, it is according to your antenna you show in the presentation. The the surface is so a round or cylinder or something. Do you have something? And yeah,
Yeah.
thank you.
Yeah, thank you, Pak Purwadi. At this time, we would like to design um, a miniature, yeah, a very small one. The one that we show before about the antenna, uh, we use only into polarization. The first one is what's it? Into polarizations. That's it's not really omni at this time. But probably in the future we would like to make it omni. But currently we only have a dipole into polarization. So hopefully the size is about 1.5 until 1.5 1.2 meters and the dimension is about 1.2 meters times 1.2 meters and 1.2 meters. Yeah, a cubic, yeah. It's kind of cubic. That's the dimension that we would like to design, a small one. While the chamber itself is only 50 centimeters times 50 times 50. It's a small one. Hopefully, it can give us uh, some what's that? Proof of concept, yeah. At the first time, proof of concept whether we can generate a magnetic field, artificial magnetic field inside the chamber, hopefully. So we do use some generator, signal generator, and then we measure the magnetic around the chamber. That's actually the goal of these activities. Yeah. Thank you.
Pak Michael still muted. Sorry.
The principle of your shield is interference between two electromagnetic field, or you want to you
Induction,
ya apa
yeah.
merubah arah dari gelombang itu,
Uh,
to change the trajectory of the wave.
yeah. The first one is to by using polarization, we would like to diffract the incoming signals. So we reflect the signals out. And the second one is for some signals that are positive, are useful, we would like to absorb. So that's the reason why we would like to have like meta materials that we can polarize. Yeah, we can polarize the surface, and then to reflect unused signals and to absorb the useful signals. I think that's the idea.
Okay, thank you, Pak.
Thank you, thank you.
Thank you very much for the question and answer. Is there anyone else that want to have a discussion with Pak Reza? If not, I think we will close this session, this speaker and the discussion session. Maybe I will give a brief summary for this event. So as we all know that Mr. Mitsunari Ozaki does a research in scientific observation at the Showa station in Antarctica and the surrounding areas, and he's doing some research about the energetic plasma via wave particle interaction, and his research is about the plasma environment may have a relation to the atmospheric chemical balance. And thank you very much once again for the speakers today, for Mr. Mitsunari Ozaki and also for Pak Reza Septiawan. And we really hope that we will have a collaboration research with Mr. Ozaki in the future. And maybe Pak Budi can be our mediator later for our collaboration research. And also, I would like to thank to all of the participants for the contribution in this event and for the discussion and everything. And I think it's time to give back to Mbak Kristanti. Thank you very much for the time.
Thank you,
Okay.
Marcel.
Yeah,
Thank
we
you.
would like to thank you to Ibu Marcelina and all the speakers, Mitsunari Ozaki Sensei and Bapak Dr. Insinyur Reza Septiawan for bringing us a very productive session today. So ladies and gentlemen, we are now in the closing session. We would like to remind all of you that the link to the attendance report form is now available and active. The link has been embedded in the chat column. And on behalf of the committee in charge, we would like to express our apologies we made during the event, and thank you very much for your active participation today. And have a great day. See you again in the next program. Wassalamualaikum warahmatullahi wabarakatuh.